So SAFOD's really been at the forefront of this idea of drilling through active plate boundaries, and there's been this proliferation in fault zone drilling in the last couple of decades. And I think I was still in grade school when the idea of SAFOD got started, so I'm probably not going to talk about how it got started so much as what we've seen, some of the interesting results that have come out of it, and how it's led to some other work at other plate boundaries. I want to start with why we drill through fault zones to begin with. And really we want to learn about the physical and chemical processes that control deformation at seismogenic depths where earthquakes nucleate. And the sort of first order science that we'd like to do in this kind of situation is investigate core material, actually look at the fault, look at its geology and its structure, without any overprinting of exhumation or weathering, which is something we always have to deal with at the surface, as well as measure the in situ conditions that determine the stress state on the fault, things like stress and pore pressure and permeability. So that's sort of the, if you drill through, that's one of the things you can get if you've been successful at getting core. The sort of next step down the line would be to install a more long-term observatory to look at changes in any of those conditions, those stress conditions on the fault during the interseismic cycle. And sort of the final and maybe the ultimate, the hardest part to do would be to actually capture an earthquake. So to really learn something about the rupture process by observing the fault at really close quarters. And the site at SAFOD was chosen for all of these reasons. It is located at the southern edge of the southern end of the creeping section of the San Andreas, which deforms through mostly aseismic creep and micro earthquakes. And it had this one really nice patch of repeating earthquakes that was reachable. It was feasible to reach that through drilling. So that was part of the reason that the target was chosen. Another one is that this area, this region had been sort of the focus of a long-term debate about what controls, about what is the strength of plate boundary faults. And there were regional heat flow observations or a lack of a heat flow observation, as well as stress orientations along the fault that were nearly perpendicular to the fault that suggested that the San Andreas was quite weak in this area, like sustaining shear stresses of more like 10 MPa than something more like 100 MPa, which is what we would have expected at the time from laboratory experiments. So this looked like a target that was ripe for learning something new. So why could the San Andreas be weak at Parkfield, or really why could any fault be weak? The shear strength, as we know, is determined by the coefficient of friction of the material in the fault zone, as well as the effective stress on the fault, which could be modulated or could be lowered by very high pore pressures. So those are sort of hypotheses going in. So this is a cross-section of the drilling at depth. Drilling occurred in a couple of different phases, or 3 phases, with the third phase involving coring through the fault zone. Lost my mouse. Anyway, you can see it there in blue. And the coring during the third phase found that through casing deformation of the hull, that there was 2 active strands that had been drilled through it that had been dubbed the southern deforming zone and the central deforming zone. So the actual active part was definitely captured, and lots of great core has been brought up. This is just a picture of one of these, across the core from across the southern deforming zone. I couldn't even start to talk about all the results that have come out of the SAFOD core, so I'm not even going to try in 15 minutes. But this work is ongoing, and results are still coming out, and actually core is still being distributed. Right now there's a call for, or you can apply for more, for samples again. There's a new sample request open. So I'm going to highlight something that I find quite interesting, and that's the results of the frictional studies. Why isn't this moving? There, all right. The frictional studies of the core. And So this is from multiple groups. The plot on the left, the Carpenter from the Penn State group, as well as the Lochner's lab from the USGS. What we're looking at here is the coefficient of friction here, and this is actually offset so that these are the same values on this plot. And the Carpenter plot is showing a distance from the central deforming zone, and Lochner is showing both the central and the southern deforming zone. And what really stands out is that these active deforming zones are much, much weaker than the surrounding wall rock. As you can see, that has more like coefficient of friction around 0.6. And inside these active zones, you get something more like 0.1 or 0.2 friction coefficient. And it's important to point out that, Carpenter has highlighted here that to explain the heat flow, or the lack of a heat flow anomaly, you would need friction of something like 0.2 or less. And to explain the stress orientations being nearly perpendicular to the fault, you would need a coefficient of friction below about 0.1. So these data are showing that you can actually explain the observations from the surface by these very, very low shear strengths. So in addition to that, during drilling, no high fluid pressures were found along the fault. So it seems like we can knock that idea off of the table, that it really looks like the materials within the fault zone are what's controlling how weak it is. And I should highlight, these are the weakest fault zone materials that have been found to date, I'm pretty sure, although somebody can correct me if I'm wrong. This is a static coefficient of friction, not something that's slipping at coseismic speeds, which we know can also be around the same friction coefficient. And then in addition to that, another thing that came out of the core was that there was evidence for pervasive pressure solution. So not all of the deformation needs to be frictional either. So there can be stress relaxation through viscous processes. So that's sort of a rapid view of what we've seen from the core. So getting on to the second step in fault zone drilling, installing observatories. So a seismometer array was installed at SAFOD, and it worked for about a month and was recording some very nice looking earthquakes, as you can see, but then it had some technical problems. Now there's one geophone in the hull, and I'm sure we'll talk a lot at this meeting about what should happen next, or what could happen next. So then I want to switch gears a little bit and just talk about some other fault drilling projects. And this list is by no means exhaustive. This is just sort of things that I came up with. So I'm sure there's some that I missed, and it's vaguely chronological, starting from some things that happened a very long time ago to things that are still in the proposal stages. But these drilling projects tend to break out into two separate groups. Some are like SAFOD with a sort of more long-term drilling at seismogenic depths in mind. And some are more, when you have a big earthquake, you rush in and drill and you do sort of a post-mortem on the fault. And that's true for the Nojima and Chilungpu faults. They recovered core after those big earthquakes. And I'm going to talk a little bit about the Wenchuan and the Tohoku earthquakes, where there was actually, the drilling response was rapid enough to actually look for temperature decay after the earthquake, so that we can actually say something about the coseismic coefficient of friction on the fault. So JFAST was an ocean drilling project that happened about a year ago. The site is located within the patch of the Tohoku earthquake that slipped approximately 50 meters. And it successfully retrieved core, including through the décollement, which ends up being, they got about a meter of core through the fault, and it can't be any wider than about 5 meters, given their recovery. So it's a very narrow plate boundary. And at the time, they also installed a temperature string to record that temperature decay. And just a couple of weeks ago, so after some heart attack-inducing inability to find the hole, they returned and just a couple weeks ago recovered the temperature string. And you can see the happy scientists there. So look forward to those results coming out probably pretty soon. I should say, though, that work that's also underway on the core, if you saw any of this at AGU last year, the friction experiments coming out of this core also indicate that it's quite weak, sort of more like San Andreas weak. So the Wenchuan earthquake in 2008, the Chinese government drilled through that fault pretty rapidly after the earthquake occurred and again installed a temperature string. And here's a picture of the temperature data, and it's pretty flat. And there's a possibility that there's a very small anomaly down in the corner here, but really there's really not much of a temperature anomaly. And if you model that, you'd find that that requires the coefficient of friction during the earthquake to be below 0.05. And if this doesn't actually end up being an anomaly related to the earthquake, then it has to be even lower than that. So it's sort of a fascinating result. So those were all post-mortem, so sort of post-earthquake kind of work that you could do. What about that third point on my plot, or on my original slide, saying, what about capturing a fault as it's slipping? Like, are we ever really going to be able to do that? Like, we know that earthquakes are so hard to predict. And even if you do have a good sense of when it was going to happen, you're subject to, errors in your earthquake locations, and these things are very hard to do. So this is in the proposal stage, but I think it's a great idea, is to drill through a repeating slow slip patch off the North Island of New Zealand. So you can see here these green contours are showing one of these repeating patches with the drilling target shown here in the star. And it's occurring right between the transition from a lock to a freely slipping subduction zone. And so the idea here will be to core through the subduction zone and then sit there and wait for one of these events that seem to be occurring about every 2 years. And it's not the same as capturing an earthquake. We won't learn anything about the earthquake rupture process. But we actually don't know anything about the slow slip event process either. So we're bound to learn something by doing this. Okay, and so finally, when Ramon called me, he said, just get up and say something interesting, because I actually haven't worked on SAFOD myself yet. So here's a potentially career-ending slide. One thing that I have been working on lately, and I think probably everyone in this room has heard something about, and the EarthScope actually has played a very large role in, because we couldn't have done this work without the transportable array, is this uptick in induced seismicity that we've seen in the Midwest in the last few years. And I'm not suggesting one of these targets per se, but I want to highlight that we've learned a lot about how to trigger an earthquake through fluid injection in the last few years, and how geology of the site can play a role. So I don't want to suggest a site necessarily as much as an idea of having something like a SAFOD meets Rangeley experiment, and maybe we don't want to sit around and wait to capture an earthquake. So I'll end it there, and I'm going to plug an upcoming ICDP workshop on fault zone drilling that's happening at the end of the month in Utah. So thank you very much.